Welcome to the last video. Congrats, you made it on radiometric dating. All right, let's go. So just think to yourself for this one, true or false? When a radioactive atom decays, it becomes a different element. And that is true. Radioactive atoms break apart. Usually they'll lose a proton or they'll gain a proton, and that makes them become a different element. All right, let me just shrink my head here. So this is from the previous lesson. When an atom breaks apart because it's unstable, we call that radioactive decay. Okay, so an example is uranium breaking apart and becoming thorium. It went through radioactive decay and it became a new element. All right, we don't need to go through that. So think about things that are really old, right? How do we figure out how old they are? And a lot of people have heard about carbon dating before. So this lesson is about things that are like carbon dating, right? This is a picture of the oldest known tool. So at a site in Kenya, we've found things that we think are early versions of hammers, things that they used to cut things, and even some anvils. And so these tools are around 3 million years old. And the oldest human fossil is a jawbone that we found in Malawi, and it's around 2 million years old. So pretty old stuff. How do we figure out how old these things are? That's what today's about. Okay. So let's think about a rock and let's pretend there's some radioactive atoms in there, which many rocks there are. Okay. So the atoms in these rocks that are radioactive go through radioactive decay. So the alpha decay and the beta decay we talked about before. Okay. So this is an atom inside the rock. It's unstable, so it's going to spit out a part of the nucleus and become a new element. Okay. And so these radioactive atoms, they actually change into different elements as the rock gets older, right? Because as more time passes, more and more of those atoms are going to be changing. So let's just pretend this rock was 100% uranium when the rock got made. That's not actually true, but we're just going to pretend, okay? So when the rock was born or made, it was 100% uranium. And then over time, some of that uranium became lead. Okay, so if we found like two different rocks, we would know that this one's probably older because it has more lead in it. All right. So the element that the atoms are before they go through that change, we call those the parent elements. So in this case, uranium here would be the parent element. Okay. The daughter element is whatever element those atoms turn into. So in this example, that's lead. So daughter element is the element after the atoms change. Your first learning target is to explain what an element's half-life is. Okay, and I'm going to tell you right now. So half-life, and you can remember this by the word half, it's the amount of time it takes for half of the atoms in an object to change. So in this example, a rock. However long it takes for half of those atoms to turn into lead, That is one half-life. Okay. In other words, a half-life is the time it takes for half of the atoms to change into the daughter element, if you want to get technical about it. Okay, so in class we did an activity. Every person had a die, or a dice, if you will. And we all threw the dice, and if you rolled a 3, that meant you turned radioactive and you turned into another element, so you had to sit down. And we all just kept rolling our dice until half the class was sitting down. And then we said, however long that took, that was one half-life, because half of the class changed into a new element. Okay. So why do we care about half-life? Well, if we know how long it takes for half of the atoms in a group to change, we can figure out how old that thing is. Okay, so we're going to use carbon as an example. If you've heard of carbon dating, this is what carbon dating is. So let's say we found an old skull from a saber-toothed tiger, and we want to know, how old is this? Well, radioactive carbon turns into nitrogen. We know that, and we know exactly how long it takes for carbon to do this. Okay, so we could look inside the skull and say, how much carbon is there and how much nitrogen is there? And use that to figure out how old the skull is. We're going to just pretend that this saber-toothed skull was 100% carbon when the animal was alive and right when it died. That's not actually true, but we're just going to pretend that, okay? We know that it takes 5,730 years for half of the carbon atoms in something to change into nitrogen atoms. All right, so if we found the skull and it was 50% nitrogen, like half of the carbon had changed into nitrogen, we would know that the skull is 5,730 years old. All right. So what if we found a skull that was not half carbon, but only 25% carbon? Well, that means 2 half-lives have passed, because we went from 100% carbon to 50%, which is half, and then half of that is 25%. And so it's gone through 2 half-lives, and 1 half-life is this 5,000 years. So if that happened 2 times, we would know that this skull is 11,460 years old. Okay, so yeah, every time half of whatever's there changes, that means a half-life has passed. So we started with 100, we went to 50, right? We cut that in half. And then if we cut the 50% in half again, that's another half-life. Okay. So that's my question for you, even though I just told you the answer. Think back. How many half-lives has this skull in the middle been through? That is a question on your note sheet. And the answer is 1 half-life. Okay, if I asked you, how many half-lives has this skull on the right gone through? You would say 2, because we've cut the amount of carbon in half twice. Okay. So this works the same for every other element, not just carbon. And this technique of using the half-life to figure out how old something is called radiometric dating. Just think like radioactive, right? We're trying to date something, figure out how old it is by using the radioactive atoms. So like I said, there's different kinds of elements we can use for this. We can use carbon. We can use potassium. Radioactive potassium turns into argon. And we can use uranium, which eventually turns into lead. And each element has a different half-life. So what this is showing is, for example, uranium turning into lead, that takes 704 million years for half of the uranium atoms in something to turn into lead. It takes that long. Okay. And this never changes. It's always that long. For iodine, radioactive iodine, to turn into the element xenon, it takes 17 million years for half of those atoms to change. Okay, so you can see some of the elements have really long half-lives, like rubidium turning into strontium, 49 billion years. That's older than the universe. Okay, this you don't need to know. This was just for fun. And then we did an activity, which you also don't need to know, is really just practice using math. So if your note sheet is filled out, then you are done. And good job.